Good morning, everyone. So, I am the last speaker of this conference. Moving forward, I am looking forward for this talk, presenting this talk to you. So, initially, I had mind that I will present in some form, but later I saw that lots of participants are also from masters and PhD courses. So, I modified my talk a bit. You will hear very less about polarization. It's only about orbital angular momentum or spatial modes of light. And I'm going to present in terms of high dimensionality and more in terms of states, not in terms of field mode. So moving forward, these are the spatial modes we have: Gauss, LG, HG, Bessel modes. And these are plotted in such a way that more intensity of the color you have, so it's more intense, and the color represents the phase. So if it's a HG, if you consider one to be positive phase, other has negative. For LG, it goes clockwise or anti-clockwise, and the color will represent the intensity of the beam. So these are donut modes, higher order LG modes, which has p values also. Here I have shown some Bessel modes. So moving forward, so this is what I have set the outline of my talk. I will discuss spatial modes, and as I told you, I am going to present this talk in terms of states. So I will introduce you what are the ways or what are the operators you can use to manipulate these states. So on these states you need operators and measurement technique. So I'm going to introduce some of these topics. As in the title you can see it's turbulence. I will show you turbulence, how we can generate them, introduce them, what is their unitary operator and other stuffs. So these are the two properties that I'm going to show which is affected by the turbulence. You know, entanglement, so orbital angular momentum entanglement. I will show how we create, how we introduce turbulence, how we measure the entanglement or the Hongomandal interference. And then I will summarize my talk and I will give a bit on the future outlook. As most of you know, I joined PRL 1 year back and I have got some facilities here. So I will tell you a bit of plan that how I am going to use it. So moving forward, so this is the mode of an mode of a spatial mode, electric field. I dumped all the amplitude part here and my interested part in this term, which is IL phi, and which I can simply write as alpha L. So L corresponds to what azimuthal index we have, and all the things are here. So if I plot the intensity distribution that you saw 2 slides back, so it's the Gaussian, it has no L, so I write it as 0. You go on positive side, it's 1 to 3, negative side -1, -2, -3, and you can span the whole Hilbert space from -infinity to +infinity. So there are few things that we got. We can simply write our state like this. So unless I need this part, I will work with only this part. And these OM modes form an high dimensional states because it's not like polarization. You have only H and V, two orthogonal states. Here we have infinite. So moving forward, operations. If you have one mode, how you can convert to another mode? In polarization, you can convert from H to V by using a half-wave plate at 45 degree. Here you need a spatial light modulator or spiral phase plate to introduce the mode. So I'm taking an example of a spatial light modulator where if you want to increase the state by 3. So let's assume you have a Gaussian which has a state 0, L equal to 0. You want to change it to 3, you put appropriate pattern on the SLM and you get the state 3. So SLM, as these are not perfect devices, I also put a grating on top of it. So it becomes a fork pattern similar to this. This is for L equal to 0. And in the first diffraction order, you get your desired mode. So to operate on these states, you use a spatial light modulator. and they are very versatile. You can change the mode, you can use DMD, that's also coming up. They are fast, they work on high power lasers. So this is the spatial mode manipulation technique. In terms of measurement, whatever mode you want to measure or superposition of modes, you couple it to a single mode fiber. So if you see this integral where you see the coupling efficiency, it is the mode that you send in and the mode of the fiber. So if this is 0, so here I represent it as 0, and whatever mode you have here, that is like this. So I'll, yeah.
Generally, mode functions are very complicated. Look at a fiber or look at anything.
Yeah.
So, but you are representing with one single value?
Yes, because I wanted to be, so as I told previously, I will dump all the intensity part somewhere and I am considering only the L part.
Representative variable.
Yes. Okay. So that actually comes here if I take another, if I multiply this another Gaussian function, this is the IL5 for the input mode. For this single mode fiber, there is no L part. I can in a way write like this. So input mode is this, Gaussian is here. So they will be 0 if these two are not same. So L input is 0. So this is one of the way by which you can measure how much Gaussian you have. So by using the spatial light modulator plus this single mode fiber. So whatever mode you want to measure, you convert it to Gaussian and couple to single mode fiber, whatever you get, it's your measurement outcome. Another is if you want to give a global phase, you put two Dove prisms rotated by angle phi. Okay, so by using these techniques, if you give an input mode L, it will be converted to L and there is a phase factor outside. So these are the 3-4 operators that I can see for orbital angular momentum states. And now what is turbulence and scintillation? So turbulence is actually the velocity distribution in fluid. So if you have temperature gradient or in the hot sun you see the this air gets heated up and they move up and you can actually see the flow of that air. So I am considering this turbulence as this velocity distribution in the fluid, because if the temperature difference is there, velocity of the fluid will move. And scintillation is what happens to the light in the turbulence. So these turbulences are actually the refractive index fluctuation, because the flow in the fluid will give those refractive index fluctuations. And here is an example. If you give an input mode like this, you get the scintillated mode like this.
Another question.
Yeah.
In hydrodynamics, when you talk about flow from regular flow to Newtonian flow to this turbulent flow, you always talk about some Reynolds number. There is a critical point.
Yeah.
This optical turbulence. Can you have a
So
equivalent Reynolds number?
no.
No, you can't, right?
No. So I will actually there are many ways to introduce this turbulence or get this turbulence. So I am mainly focused on Kolmogorov type of scintillation, where you can see the two terms Cn square, which actually gives the refractive index structure constant. So the value of Cn square, if it is between 10 to the power minus 12 to 10 to the power minus 13, 10 to the power minus 13, it's very less turbulence. 10 to the power minus 12, it's high turbulence. So you can say that as sir associated this Reynolds number, I can say that 10 to the power minus 12, 13 will give you the fluid flow, regular flow, and it's equivalent. And there are other parameters. So so our turbulence will not be like just random phase function, it will be like clouds, you can say. So I will show one of the example later on. Now once you have states, you want to build multiple states like superposition of states. So if you want to have a pure single photon qubit states, so you consider A and B, which are the two basis elements from your whole Hilbert space minus infinity to plus infinity. You can consider 1 minus 1, 2 minus 2, considering the symmetry. So you can consider this, you can build your state like this. If you have qubits, you build like this so that you have normalization and orthogonality preserved. And if you want to have entangled states, it will be summation of some of them. So effect of turbulence on a spatial mode. So there are two ways to see this turbulence. As in, if you are doing an experiment in lab, you cannot have infinite number of SLMs. So what you can do is, whatever turbulence you want to consider, you squeeze all of them and consider a one phase screen. So this is called single phase screen approximation. So you consider an approximate turbulence with a single phase screen. You can also do with multiple screens if you are rich. So this is one of the turbulence pattern that I have got for 10 to the power minus 12, which is a bit higher, and it looks like a cloud. So you can see that it has a structure function. So that was the structure function that I mentioned in one of the slides. And if you give a state 1, which is a OM of 1, you can see that 1, as you increase the distance, or when you propagate more distance, you see that the contribution in 1 goes down and contribution in all others goes up. But if your turbulence effect is less, in that case you will find that your incident mode will have more intensity than the other side modes.
Is it a static turbulence or dynamic?
It's a static turbulence. It's just one of the considerations that I took.
It's fixed.
Yeah.
It remains fixed.
Yes.
Over time.
So this is not an experimental one. This is a simulated one where I took a mode, I multiply it with this function, I propagated for a certain distance, and I calculated what are the modes exist in the remaining one. And I calculated the relative intensity and I plotted. Okay. So moving forward, so this is one of the example, this is one of the calculation that I did with my summer student, where if you have some turbulence effect, you need to quantify it. So I use this parameter crosstalk, and which says that how much intensity is left in that particular mode after the turbulence. So I choose the length between 5 meter to 500 meter. I took 50 iterations because some of the turbulences you can see that it is not giving so much of effect on the mode. Some of them will give the less effect on the mode. So with the same turbulence, like if you see the clouds, if you can see that somewhere you get more whitish, somewhere less whitish. So depending upon which one you choose, you get different turbulence effect. But overall, your turbulence effect will come from the how much Cn square you have taken. So here I have taken a bit of a stronger turbulence strength. I took L equal to 1, and I saw that as you increase this length or the propagation distance in the free space, you see that higher order modes, like this is for L equal to 1 and this is the Gaussian one. So you can see that these vortices are affected by the turbulence more than the Gaussian one. So certainly turbulence has effect on these modes, and at some point of time I will show you what are the ways that I thought I will implement to mitigate them. Moving forward, so this is okay. So SI is the total intensity left in that mode versus all the modes. So this is generally 1, and these are the whatever it's left. So as you increase the distance, what will happen? So this will become closer to 1. Okay. So because this becomes 0, so as you increase the distance, the intensity left in that particular mode will be less. So SI will become 0, and if you calculate all the side modes, okay, they are equivalently 1 because you are not losing any photon here.
So one is the upper bound.
Maximum it's 1.
Right.
Yeah.
One is the upper bound.
Yeah. So that's why you can see that as you increase the distance, they are approaching 1. Okay. Yes, because whenever I do these calculations, in the mode in the end, whatever mode I get, I do the modal decomposition. So in there, I actually calculate what are the modes available with their relative intensities. I think yes, because you can see this follows like this. I didn't check how it will look like. I didn't do the for it. Yes, yes. So when I consider the Kolmogorov theory of scintillation, if I calculate the turbulence from there, that scintillation, that way has all these things implemented. Okay, so it will come from there. Yeah. So this is minus 11 by 3, it's on the K and it's minus 2 by 3. I think I need to see again. Thank you. So moving forward, I was here. So to generate these higher dimensional entanglement states, I think on the first day you heard Dr. Gautam Samanta's talk. We use SPDC process, where a spontaneous parametric down conversion process. So I'm showing you an example here. So this is the non-linear, non-collinear case where the two generated photons follow an angle. Here both of them are collinear. So in this case, the energy and momentum of these two photons, these three are conserved. So whatever it's in the pump beam, it will come to there. So as momentums are also conserved, you can say that if L equal to 0 or if I am pumping with a Gaussian one, so if signal has the OM of L, automatically the idler will have minus L. Otherwise the momentum or orbital angular momentum will not be conserved. So, so this is one of a very basic experimental schematic that I can show here. Where pump is there, it is signing the BBO crystal, which will do the down conversion process. I am separating those two, signal and idler, statistically using these 50-50 beam splitters, separated them. I am using two spatial light modulators. So whatever mode is generated here, I will convert them to Gaussian and couple to single mode fiber.
So I was asking the same question to RB.
Okay.
So why always you do this thing before down conversion? Why don't you convert it into a wave mode, then you down convert that wave mode?
Yes, so there are, okay, so there are many examples even we are doing where we pump the crystal by using an OM mode. So there also the,
You are using a linearly polarized, right?
yes.
So why don't you do with this wave pumping?
Depending upon the requirement, like in one of the recent experiment, as RP told, that Sarika is doing with some experiment. So there we actually pump the crystal by using a superposition of LG mode. So LG 0 2, so 0 is the OM and 2 is the as this radial index, then 0 0 and minus 2 0. So L azimuthal index is minus 2 and
My question is slightly different. You use one wave mode, it is getting down converted. If you are having orthogonally polarized, right?
yeah.
One is possibly one is right circular, other one is left circular or something. I don't know.
Both are linear.
You can control that.
Yes, because this BBO crystal, if you give horizontally polarized light, the two down converted photons will be vertically polarized light.
Okay.
You can design the pump depending on the requirement. You can, so we pump with many superposition of beams also. And accordingly we get the quantum state. So
All
that
these experiments I see, they do the after
Pump
down
is
conversion,
independent.
they convert them into wave.
Yes,
Not the original, not the
because our BBO, it has an inherent filter inside it, like a linear polarizer. So it can only down convert to one certain type of, even if we give circularly polarized light, it will take only one of the component and it will down convert because of that. Okay, so this is one of a very simple setup for OM entanglement, and as I can do, I can scan this from -10 to 10, I can also scan this from -10 to 10. So this, you calculate how much coincidences you are getting, you plot, and this is what you get. And this shows that there is no correlation between different modes. So this shows that your orbital angular momentum is conserved, and if you take this SPDC state and it's the superposition of all these states, and as sometime back I told you, I do not worry about the intensity part, and here I worry about the intensity part because all the intensities are not same, and this actually comes because you have a Gaussian beam, it has a finite size, so it cannot generate very high order mode effectively, and also from the SLM that higher order modes to Gaussian conversion is a bit difficult. So these two things actually lead to the lower intensities on the two sides. And here also you can have this type of integral where a signal idler you can write simply like this. So either you get unless Ls equal to minus Li, you do not get any intensity out, and this also shows from your this OM spectrum. So
This linearity is just a consequence of the charge conservation.
yes, from the crystal, yeah. Because one photon is down converting to two, so certainly the orbital angular momentum should also be conserved. Okay. So coming to the requirement, okay. So yes, so qubit, several experiments have been performed with the qubit that if you introduce turbulence to one of the photon, and if you study in qubit, it's known that as you increase the order of these vortices or the states, you will get lower, as you increase the turbulence, higher order vortices are affected more. So we wanted to go with higher because as OM gives us the freedom of high dimensionality, we go with Q-treat. So we build our state like this, and due to our symmetry, like our pump was Gaussian, I choose this type of Q-treat state where we have L equal to -1, 0 and 1. So -1, 0 and 1, or -2, 0, 2, -3, 0, 3. And as this is a Q-treat states, we use do the quantum state tomography, and finally we calculated the negativity to find out what is the effect on the negativity or the measure of entanglement with the turbulence strength. So this was the setup. So in one of the SLM, I am not introducing any turbulence, so my state was like this. In another one, I added the turbulence. And this is the state, this is the way by which we calculate the mutually unbiased basis. Like in polarization also you handle H and V. But if somebody choose this basis, and if other person measure in diagonal anti-diagonal, he will have no correlation what was there in the horizontal and vertical, because it's just equal superposition. So you also need to measure in mutually unbiased basis, and these are the density matrices that we obtain. So when there is no turbulence, we defined by W. So when there is no turbulence, it's all okay. As you increase the turbulence, the intensity goes also in the other states. And as you, okay, so in density matrix, when you plot, you have these states, -1, 0, 1, and then you have one of the mutually unbiased basis. So this intensity actually correspond how much state is there, like HH and VV, similar to that. And we plotted the negativity for all, for the different Q-treat states that we put, and we saw that as you increase the turbulence, the negativity decreases, so entanglement we are losing. This is one of the theoretical plot where we calculated which modes are highly favorable. So as we can see that the Gaussian one, in the higher turbulence, they are getting more affected with the means the higher order modes are getting less affected than the lower order modes. So you can see that L equal to 1 at higher turbulence strength, you can see the negativity is less than the other two. So this is only the theoretical plot, as in our experiment the error bar was more, so it was very difficult to observe in the experiment. Moving forward in the Hongo-Mendel interference. So as some time back you heard about Hongo-Mendel interference, where on a beam splitter if you send these two photon signal and idler, you have four possibilities. So both will be both will go in one path. So these are the two possibilities, and they will either transmitted or reflected. So these two possibilities, and due to the phase gain there is a minus sign. So these two get cancelled out and you get only these two possibilities. So Hongo-Mendel interference will say that if you have two identical photons, they try to bunch them and they go in the one path. So if you measure the coincidences in the two arms, you should not find one. So this is one of the plot where if you match or if you try to make them identical, so at the point of like when there is no gap between these two photons, you find that the coincidences are null. So as these turbulences, we associated these turbulences with a turbulence matrix, and we try to find out how this state, which is one of the state like 1 minus 1 plus minus 1 1, how this state will be affected by this turbulence operator. So first task was, let's associate this turbulence to only one of the photon. So we operated on only one of them. So my photon A is getting affected by the turbulence, but with B its identity matrix, so no turbulence. So when we do this calculation and try to find, so this is the complete state, and from here which states can give me coincidences, because in the end I am going to measure 1 and minus 1 only. So or 2 minus 2, 3 minus 3. So this type of a state will give me coincidences, and these two elements are equal because it's similar probability for any turbulence strength or any turbulence to give 1 to any other mode or any other mode to 1. Okay, so that's why these two elements are same, so they will not give you any coincidences. So here your turbulence is not going to affect your Hongo-Mendel dip. Your visibility will always be perfect. But when you do for both of them, it seems like they will start filling up your dip with these, because your cross terms A12 and U12, they are coming up. So this is how I build my setup. So these two SLMs were giving the turbulence to the two photons. So then they are matching on this beam splitter. These two SLMs are measuring the mode, and they are getting coupled to the single mode fiber and doing coincidences. So here I show 4 SLMs, but technically I had only 2. I used 2 parts of the SLM here and 2 parts of the SLM here. 3 and 4. So in the end you need to measure in one of the bases. So I'm measuring 1 and minus 1 only. I do not bother about like minus 2, minus 3, how they are getting affected, because I can measure only one mode of the generated photon.
So you are getting rid of the background as well as
Yes, and all other modes. So, so here I am actually showing you one of, here I have put one of the dove prism and rotated by pi by 4. So what will happen is, by using the phase that I introduced to the, by using these two dove prisms, you can actually go from symmetric to anti-symmetric states for few of the modes, and your Hongo-Mendel will act like a filter. So here, for if you do not do any Hongo-Mendel, you have this spectrum that I showed some time back, and if you have this Hongo-Mendel filter, what will happen is, for few of the states you are generating symmetric and few of the states you are generating anti-symmetric. Like 1 minus 1 will give you anti-symmetric, and 2 minus 2 will give you symmetric state. So they will give you these coincidences, but all odd number will not give you coincidences.
Am I correct if I say that only for one pair, this HOM cancels
Yes.
this coincidence measurement?
Yeah.
Only one set of modes.
Only one set of modes. So that's why these Hongo-Mandel interference, they are also known as Hongo-Mandel filter, because if you introduce noise to any of the state, it cancels out. So this was my result when there was no turbulence. All of my Hongo-Mandel scan were perfect, and if I introduce turbulence, what will happen is, if both side I am adding the turbulence, it's something like this. So some turbulence, so it's for only for one of these turbulence strength, but there are 25 number of realizations. So this is what I was talking about, like
Critical value you are mentioning, Shashi, 10 to the power minus 12.
yeah.
You work on the above side and the below side. What is the corrected difference?
So here you can say that my Cn square value was something around 0.4 into 10 to the power minus 12. No, sorry, yeah,
Below the threshold.
yes.
And did you try anything above the threshold?
Above the threshold, what will happen is your turbulence strengths are higher, so you will get more feeling here. So you can say that here it will come in the visibility part. I will show you. Okay, but it's not only this. If you increase the turbulence, you can see that number of photons in that subspace, like I am measuring in plus minus 1, plus 1 minus 1, the number of photons reaching to the detectors are less. So they are getting scattered to the other modes. So this was for the antisymmetry case. So here also photon numbers are decreasing. These were the different realizations for double-sided and single-sided turbulence. And here it goes the visibilities for the symmetry case. So it's as you increase the turbulence strength, it goes down, and this is for the single-sided, this is for the double-sided, and these are for the antisymmetry case. So as you can see that even after I am increasing the turbulence, I am not getting any effect of the on the visibility. This actually happens when your single phase approximation and multiple phase approximations are getting introduced. So even if you have one phase, you are not able to generate that much of high turbulence using one phase. So this limitation is actually coming from there. So what we found that if you have one-sided turbulence, if you are giving turbulence to only one side of the Hongo-Mandel, one of the photon, your Hongo-Mandel visibility is not going to change much, just experimentally. So in this will have application in those cases where your SPDC photons are generating from somewhere. One is going through the turbulence and one going to through the optical fiber where there are much less losses and much less turbulence effects. So in those cases you will get certainly the perfect visibility. So if you have any application where this is needed, so this study will be useful. So in summary, we saw that if you increase the turbulence, entanglement decreases. If you have one-sided turbulence, the Hongo-Mandel visibility remains same. If it is two-sided turbulence, the Hongo-Mandel visibility goes down. And coming to the future outlook, we have a 200-meter free space optical channel. So this is in the Thaltej campus. We have these two buildings. So these are the two cabins that we have built. So Alice, one for the Alice and Bob, because we are doing mostly QKD experiments there. So and on the other side here there is a reflector which is on this post on a breadboard here. So light comes from here and goes to the here, and then it's getting measured. So currently last year we have done with BB84 protocol and BBM92 QKD protocol. We are currently doing this, so these experiments are being done in the night, and we have the plan to build this, go with this BB84 with decoy protocol. So these things are happening, and experiments are going on with this channel. And my aim, if So whatever I have presented here, it's in the lab. So I wanted to test on this free space optical channel. And if I see the application of this, I want to study, like, you know, Alice, Bob and Eve. Alice and Bob want to communicate and Eve want to get as much information as they can. So one of my aim is to consider this turbulence as a Eve, because it introduces noise and it also takes photons, because less number of photons will go on the other side. So these type of studies that I am focusing on. And thank you. And
Thank you. So we have 7-8 minutes for discussions.
Shashi, excellent work, excellent direction is my first comment, but I have some suggestion.
okay.
You may heed that. See, yesterday Omar was showing a paper that was by, again, I was mentioning that thing, by this Greffe's group, Jean-Jacques Greffe in Paris, okay? And Paris, that paper I was mentioning there, what they are doing, they have introduced some losses in one channel. And once you introduce losses, it opens up a new degree of freedom.
Yes.
That's the main gist of the paper. And once you open this another degree of freedom in the problem, what happens? You have this anti-coalescence, that Hongo-Vandel deep. The statistic you can change, you can make it a peak.
Yeah.
So it will be coalescence peak and this anti-coalescence peak. So it will be very easy to introduce losses in one of the challenges in your experiment. You can see whether you have control over the Hongo-Mandel deep. Can you convert it to deep to peak? Okay, that's one thing you could try. That's a suggestion. And the other thing I wanted to ask you, if you have this thing, but see any assessment of this atmospheric turbulence, what you have, of course that is not static, and then you need to assess what is the time scales of this turbulence, so that you can consider it static so far as your device is concerned. Over the time scale, whether the turbulence pattern remains static or not.
Yeah.
Any comment on that?
So actually we have not started any experiment with OAM and in this channel. So the first thing I want to do is characterize the turbulence, what I get in the real channel and what turbulence I put in the simulation, so that my simulation will match the experiment a bit, so that I will be able to correlate the two turbulence strengths. So this is the first task that or this will form the basis of all the experiments that I am planning to do. Also, we have atmospheric science division in our in PRL. So I will get most of the atmospheric parameters on that day, like the aerosol concentration, extinction ratio, and those stuff. And I will try to correlate those aerosol concentration with the turbulence strength. So some of these studies have not been done. So I'm going to start from here.
Basically, we are taking a turbulence experimental, and we are
Yeah.
calibrating that turbulence. So we are going to use this calibrated turbulence set to do the experiment.
Yeah.
We are working along taxonomics because they do these things for an approach. So they have calibrated turbulence. So we can do.
Okay, so I can consider this BB84 protocol, and there our transmission was around 94% for 35 meter and around 75 to 80% for 200 meter, because beam diverges. And this was the values that I'm telling you, it's from the last year where some of the things were not optimized. So this year we are taking it a bit on the next level to optimize, so that we get more and more coupling and more photon, so that our experiment doesn't loses photon, it's only the loss from the atmospheric channel. So that's what we are also aiming for. Okay, so SPDC, we can easily generate 1 megahertz. So if you consider even 75 to 80%, we get so much of photons. Megahertz. That's what we get from SPDC maximum, and also our detectors can detect 1 megahertz very well. So
So that for odd orbital environment, you don't get you don't get deep, but for even ones you get.
okay, yeah. So I can actually say something like, you have symmetric state, okay, so which is L bar plus, okay, you then have L e to the power 2I L phi L bar plus, yes, okay. So depending upon, if you have L equal to 1, you get some value. If you have L equal to 2, you get another value. So your state is getting converted from symmetric to antisymmetric. And with Hongo-Mandel, you can only measure antisymmetric states because you get coincidence after the beam splitter. So for L equal to 2, it's a symmetric state, because here your plus will remain for L equal to 2, and for L equal to 1, it becomes minus. So symmetric to antisymmetric happens.
Also, this turbulence, does it lead to any beam shift?
Yes, beam shift. No, we do not consider that. We consider beam shift as it scatter to other modes.
In hydrogen, there is some effect called Magnus force.
In experiment with SLMs, we have not observed any of these. Maybe when we will do with the channel, we will observe.
Average value is zero, right? There is no overall. If you have the whatever turbulence pattern you have, you take the average, it's zero, right?
Yeah.
So
Yeah. So that comes from the Kolmogorov theory of scintillation.
So if there is no more question,
Thank you.